the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for linear algebra students who are going through vector spaces, and you've already gone through subspaces, null spaces, column spaces, linear independence in terms of vector spaces, and a recent conversation about coordinate systems. And now we're stepping into dimensions of vector spaces. This is the very first time that you should actually legitimately be using the word dimension in a linear algebra course. Normally, it gets used and somewhat abused when you talk about matrices. For example, a matrix that has 4 rows and 5 columns, we would say has a size of 4 by 5. But some people say the dimensions of that matrix are 4 by 5, but that's actually not true. The size of the matrix is 4 by 5. Dimension in linear algebra is reserved for a completely different concept. And to be honest with you, I likely have abused that language as well. So every once in a while, if you've gone through my videos, you've probably heard me say the word dimension, when really I should be saying the word size when I'm referring to a matrix, or even a vector. We're just going to talk about the concept of dimension in this video here, so it should be a somewhat short video. Prior to getting to the actual definition of dimension, we do need to introduce a couple of theorems here, and they are going to be very, very easy to understand. We'll feel as though, in fact, that we've seen these before, but we technically have not. The first one is what's called Theorem 9 in the textbook that I use. If a vector space V has a basis B1 through Bn, then any set in V containing more than n vectors must be linearly dependent. Again, you have a basis with n vectors. Then any set in V containing more than n vectors will be linearly dependent. To prove this, we're going to grab n plus 1 vectors, or better yet, we'll just grab a number of vectors greater than n from our vector space V. And that's what I state right here. We have a set of vectors, u1 through up, and that set of vectors is a subset of our vector space V. Not a subspace, but a subset of our vector space V. And the number of those vectors is greater than n, where n is the number of vectors in the basis for the vector space V. Now we want to show that these vectors must be linearly dependent. The way we're going to do this is by creating a linear combination of these vectors and showing that that linear combination has non-trivial solutions. In fact, let me write that off to the side. So there we go. We want to show that linear combination equaling 0 has a non-trivial solution. If it has a non-trivial solution, then those vectors by definition must be linearly dependent. Now, the requirement that you have already seen coordinate systems is critical here, because I told you these vectors are from a vector space V, but I did not tell you that that vector space is Rn. It could be a very abstract vector space. What's going to help us here is to transition these vectors right here into a more familiar vector space. And luckily, we can do that. So these vectors being a subset of the vector space V, and if we're given a basis for V, B1 through Bn, which we're going to call B, then we can write the coordinate vectors of these vectors with respect to that basis B, and those coordinate vectors are going to be a subset of Rn, because again, our basis has n elements. Now that we are working with a set of vectors in Rn, it's a lot easier to do our work. Now think about how many vectors we have here in Rn. We have p vectors, and p is greater than n. We have a theorem from the past that says if a set contains more vectors than there are entries in each vector, then the set is linearly dependent. Therefore, this equation, this linear combination of the coordinate vectors, must have a non-trivial solution. However, if you followed my lectures, you know that I keep an ongoing list of critical theorems that we've learned up to this point in our course. one of those theorems, which is probably not on this page, but rather on this page, is going to really help. Specifically, this last one right here. If U1 through UP are vectors in a vector space V, and if you have constants C1 through CP and there are scalars, then the linear combination C1 times the B coordinate vector of U sub 1 plus all the way down to CP times the B coordinate vector of U sub P is going to be the B coordinate vector of the summation. That is, we can rewrite this equation as the B coordinate vector of the linear combination that we're actually interested in. Now at this point, it's very important to realize that this zero vector right here is actually, because it's equal to the B coordinate vector of this sum, it is identically equal to the weights needed in the linear combination of the basis vectors to get that interior argument. That's the whole definition of a B coordinate vector. So again, the B coordinate vector returns a vector of weights that would be applied to our basis vectors in B to get the vector that's on the inside of these brackets. But that linear combination of the basis vectors on the right is just 0 times each of those vectors. It's the zero vector. However, we said something about those constants C. They started way up here. The fact that this set contains more vectors than entries in those vectors, we know that this equation has a non-trivial solution. That is, C1 through CP are not all 0. And by the way, those are the same C1 through CP we've kept this entire time. What this means is that that equation right there has a non-trivial solution, which means U1 through UP forms a linearly dependent set. And that's the end of the proof. We have proven that if a vector space V has a basis with n vectors, then any set in V containing more than that number of vectors must be linearly dependent. And that conceptually should make sense to you. If I only need 10 vectors to build a space, adding another vector is going to be a redundancy. Now this theorem I'm actually not going to prove because it's usually pretty short and it's in a textbook, so I just don't prove it here. But if a vector space V has a basis of n vectors, then every basis must consist of exactly n vectors. This is really just locking down our language quite a bit, so that if you know you have a basis with 10 vectors, every basis for that space has 10 vectors. If you add another vector to that set, it's now a linearly dependent set. This kind of harkens back to a lot of what we've done in the past, so this should not be any bit of craziness to you. And we finally arrive at the dimension definition. After weeks upon weeks of linear algebra, we get here, and you needed a lot of that linear algebra to actually start talking about the dimension of a space. This should tell you how interestingly detailed mathematics has to be. You really have to be very precise with all the definitions that you build, all the theorems you include, because many of our definitions and theorems require some high-level content. So therefore, going through in the order with which that content is introduced is incredibly important. Anyhow, if you have a vector space spanned by a finite set, then V is said to be finite dimensional. So if you have a basis that only has 10 vectors, you have a finite dimensional space. The dimension of your space, written as dimension of V, is the number of vectors in a basis for that space. The dimension of the zero vector space is defined to be 0. And that's just needed for some theory and proofs. Generally, you don't even need to define the dimension of the zero space. But if you don't define it, you just might run into a problem when you are doing a proof involving the dimensions of vector spaces. So it's nice to have that defined. By the way, if V is not spanned by a finite set, first of all, that's got to be pretty hard for you to imagine, but it's actually not too difficult to create. But if it's not spanned by a finite set, then V is said to be infinite dimensional. If you want to think about a set that is infinite dimensional, think about a basis for the set of all functions. You say, well, sine, cosine, that'll at least create all linear combinations of sines and cosines. Good for you. And then you say, well, let's take care of some polynomials. Well, I'll need polynomials of degree 0. I'll need polynomials of degree 1, 2. Oh, wait a second. I get it. I need every single degree represented, and I can't do that without getting to an infinite dimensional space. That's the issue. P sub 2, on the other hand, which is the vector space of all polynomials of degree 2 or less, is a finite dimensional space. It just has 3 basis vectors, 1, t, and t squared. But that's not the only basis, and we've proved that in the past. So let's see how to deal with this. Find a basis for the subspace and state its dimension. You do actually need to find a basis when you're stating dimension, because it's very hard to state the dimension for a subspace without finding a basis. I'll call this subspace H, by the way. I might need to reference it. Well, if you grab any random vector from this set of vectors, which we're being told is a subspace, so I'm pretty happy with that. Well, if X is from that space, then I know that X has the form A times this first vector plus B times this second vector plus C times this third vector. I'll go ahead for the time being, call those vectors V1, V2, and V3. Now, if all vectors in X are generated from those 3 vectors, you might think, well, then V1, V2, V3 forms a basis for the vector space H. And remember, subspaces are also vector spaces. That's why I just called it a vector space. However, to be a basis for a vector space, these 3 vectors not only have to span the space, but they also have to be linearly independent. So we need to showcase that they're linearly independent. There's a couple ways to do that. One is to create a matrix from those column vectors and solve AX equals 0. Basically find out how many free variables there are in that equation right there. And that's likely going to be what most people will do. But if you just pay close attention, a quick cursory glance at what you're given, you might be able to see that V1 and V3 are highly related. In fact, V sub 1 is actually -3 times V sub 3. And because of that, the set V1, V2, V3 is linearly dependent. Yet it does span our space. Well, luckily, we have a theorem from the past that says, well, if you have a set of vectors that create a subspace, and if one of the vectors in that set is a linear combination of the remaining vectors, then the set formed by removing that offending vector still will span our subspace. And honestly, I consider that to be one of the more obvious theorems. So if I remove the offending vector, I'm going to remove V sub 3 here. And that tells me that the set V1, V2 spans H. Also note, V1 and V2 are actually linearly independent. In other words, V2 is not a multiple of V1. And I wrote that here. Since V1 is not a multiple of V2, the set V1, V2 is linearly independent. It spans the space. Thus, it's a basis for the space. And remember, by definition, the dimension of H is going to be the number of vectors in any basis for that space. And all bases for this space will have the same number of vectors. So we have a basis with 2 vectors, hence the dimension of our vector space is 2. And a lot of people look at this and go, wait a second, but each of those vectors has 4 entries. It doesn't matter how many entries they have. What matters is how many vectors build the space. What's the smallest number of vectors that are linearly independent but still span your entire space? That's 2. Therefore, the dimension of this vector space is 2. And that is why dimension is not used when you're talking about the size of a column vector or a matrix. These column vectors are size 4 by 1, but as a space, the vector space H has dimension 2. Let's do one last example very quickly here. We're going to find the dimension of the subspace H of our cube spanned by these 3 vectors, which equates to finding the number of basis vectors for this subspace H. Well, since these 3 vectors span H, a subset of these, maybe even all 3 of these, forms a basis for that subspace H of R cubed. But we'd really like to know, are these 3 vectors linearly independent? We have many ways to determine this at this point. You could, technically, put these in a matrix, augment it with the 0 vector, and then find out if you have a free variable. And if you do, then you know that this set of 3 vectors is linearly dependent, and you can remove one of them by the spanning set theorem to arrive at yet another candidate for a linearly independent set that spans H. Another way to showcase that these vectors form a linearly dependent set, or a linearly independent set if they do, is to place them in a matrix and take the determinant of that matrix. If that determinant is equal to 0, you immediately know the matrix A is not invertible and that its rows form a linearly dependent set, and so do its columns actually. And this is what I'm going to do. So we get that the determinant of this matrix is 0, which means that these vectors are linearly dependent. And the fact that there's only 3 vectors here makes it kind of easy. I could just remove one of them to leave 2 that are linearly independent. So I'll go ahead and just remove this last guy. And note, these 2 vectors are definitely linearly independent because they're not multiples of each other. So I have a linearly independent set that still spans the subspace H, because again, by the spanning set theorem, you can remove a vector that causes linear dependency from your set. Since we're left with only 2 vectors, we know that the dimension of H is 2. So we have a 2-dimensional subspace of R cubed. Something I need to draw your attention to before we step away from this video is, yes, that's a 2-dimensional subspace of R cubed. There are 2 basis vectors, so it's going to build a plane in R cubed, a 2-dimensional plane in R cubed. Kind of a neat concept. Anyhow, so I hope that this gentle introduction to dimensions of vector spaces was pretty okay for you, and I hope to see you in future videos. Have a great day. Be good, human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.